Okay, we're back, and I wanted to give just a few physical examples of what we mean by simple harmonic motion. Simple harmonic motion is a type of periodic motion, but there's a kind of a twist to it in the sense that a spring is actually, kind of like the main piece of simple harmonic motion, it's the poster child. Harmonic motion is when it's periodic, it's an oscillation, but it tends to have a restoring force which is proportional to displacement. So a typical spring, or even like a rubber band, you could do this at home, the more you stretch it, the stronger the force. And for an ideal spring, its force is the spring constant multiplied by x, multiplied by your displacement. And as we're going to find out in class with the math, it leads to a certain type of equation where ma is equal to minus kx, and the solution to them is going to be sines and cosines. Kind of makes sense. If you want to describe a periodic motion, you probably want a periodic function. So think of like a sine wave or a cosine wave. Your position as a function of time for harmonic motion would actually be a perfect sine wave, for example. So some of the things that come into play, when I get this spring bouncing here with this relatively light weight on it, kind of get a sense of the period, okay, the frequency. How many times a second is the thing bouncing? Now for the same spring, I could take a larger weight, larger mass. Hang on there. Of course, it stretches quite a bit more, a new equilibrium position. But get a sense of the period. Okay. It's much slower, even though you have the same spring constant. And think it through. Does it make sense conceptually? The more mass, the more inertia you have. And so for basically the same force, you don't have the same acceleration. Okay? You have smaller accelerations for bigger masses. If you have a smaller acceleration, that means a longer period, okay? Less frequency than you would if I replaced that with the light mass. Which bounces quite a bit quicker. Okay, a shorter period, a higher frequency for that. Less mass is just easier to move, and you can move it quicker. Okay, so that's harmonic motion, just that oscillating spring up and down, or if it's sideways, side to side, just bouncing back and forth. Something that's related, now a pendulum, of course, is also a periodic motion. Make clocks out of it, for example. Technically, and we'll see why in class, technically it's not simple harmonic motion. Okay, the restoring force isn't exactly related to the angular displacement that you give it. Instead, what you're going to see when you have things that can swing, whether it's a normal pendulum where we ignore the string, okay, massless string, and it's just a little point mass at the end doing circular motion, or if you had an actual object like a stick, I could hold this and turn this into a pendulum. It's called a physical pendulum. Okay. We'll learn how to do that too with rotations, where gravity creates a torque on it, and that makes it go. Anything that swings like this through an angle, what we're going to see in class to approximate it as simple harmonic motion is the small angle approximation. So you'll actually see in problems, if I just lift this and let it swing through a small angle, then we can consider it to be simple harmonic motion. But it's not exactly, it's a pretty good approximation. Something else that's harmonic motion, think of like a tuning fork if you're a musician, or a diving board. Okay, I can take a meter stick here. Put part of it over the end. You can do, if you have a ruler at home, you can do the same thing. I press down on it and make this part oscillate. It has a certain pitch to it. That vibration is actually harmonic motion. Now notice if I make it longer, much lower pitch. Okay, it's a slower frequency, a longer period. And if I make it short, this is kind of indicative of like similar to um, uh, think music, okay, strings, a violin or something like that. You can make the length of the violin string longer and shorter. You can change the pitch. You can change that vibration. That would be simple harmonic motion of that string. Okay. One other example, if I put this weight on here, if I twist a rubber band and let it go, it oscillates back and forth through rotation. We call this a torsional type motion. Torsion is a force or a torque that can make something rotate like this back and forth. This actually would be simple harmonic motion when we have torsion. Maybe you do this if you sat on a swing at a park. If you twist up the swing and let it go, you kind of rotate back and forth. That's a torsion type experience. So all of these are simple harmonic motion. Okay. Pendulums, at least, are approximately simple harmonic, but for us, we'll consider it. The spring is really the thing to have in mind, that perfect oscillation back and forth. You can put marbles in a bowl. Think potential wells, right? The potential well, potential energy graph of a spring is a perfect parabola, okay, an actual well. And a marble in that would just oscillate back and forth. That would be simple harmonic motion. It's oscillating around an equilibrium position. It's changing potential and kinetic back and forth into each other as it oscillates. It's stable equilibrium. Okay, the bottom of the bowl doesn't leave like the top of a hill it would leave. All of these old ideas are coming back to us as we try to explain and understand how things oscillate. This will be our last unit for the year. And and so after you're seeing these examples, we'll get to the math part of it in class. And until next time, we'll see you later.